So I'm here to give you a fresh look at trampolining, and my key point is going to be that trampolining is not just a cool one-off trick, it's rather a systematic and natural member of a whole family of compiler techniques, which no doubt you're familiar with, like continuation passing style, defunctionalization, and tail call elimination. So I'm not here to claim that trampolining is useful or under what conditions, or that you should use trampolining or under what conditions. I'm just here to give you this new perspective. So actually, I'm going to give you two perspectives. And number one is kind of definitional, and number two is some more juicy bits. So if you're already kind of familiar with the terms here, you can jump back in. You can tune out and jump back in for number two. But the first one is that a lot of these compiler techniques are about moving control flow to data. So here's a simple recursive program on structure of a list. And so what we're doing is we're duplicating each element of the list. So we say, well, if there's actually a head and a tail, you cons head, and then duplicate everything in the tail. And if I'm compiling it to some sort of imperative underlying language, this is made up in the language in blue, I might do something like, well, var x0 equals the result of a recursive call. And then after I have that result, what I'm going to do as the second last step is to say, well, const 2, and then x0, and then return that thing. And then recursively, again, the first step of my recursive call is to recurse on the 5. And then after I have the result, second last step, and last step, and so on until I reach the base case, which returns an empty list, and it goes back through the stack. So let's look at this first case of recursion again, the first level of recursion. What if I took, and so what I'm going to describe is just continuation passing style that is not trampolining yet. But what if I took that second last step and moved it into a function parameter for my recursive call? And now it becomes a lambda, which says, what do I do after I have the result? And so this is the essence of whoop. And I can do this further. I can do it one more time. And I accumulate a bigger continuation, and I keep going. And this is the essence of continuation passing style, right? I'm moving something that used to be control flow, which is exactly, I'm moving something that used to be this second last step, and I'm moving it into the data, which is now this closure that's being passed around as a continuation. And now I realize that, well, the only thing I'm doing after I get this recursive value is I'm returning it. So I might as well just make it return. And so yeah, this is CPS, this is the essence. And now what is trampolining, right? I'll take this one step further. I say, I want to move even more control flow to data. And so this is the program I have. And I notice that I have some control flow in the form of function calls, and function calls are control flow. Let's eliminate function calls by saying, instead of making a function call, I'm going to return a data structure that says, oh, I want to make a function call. So I'm going to call that, define a struct called tail call. It has two components, function and arguments. I say, well, return a tail call dup each on argument, and inside the lambda is another tail call of k on some arguments. And to run this, I need an executor, again in my fake imperative language, which says, while I have a tail call to do, well, then apply the function to its arguments and then repeat until you actually get a result. And this is exactly trampolining, right? And let's look at what this execution looks like. So if I say execute of tail call at the top level, and my top level is an identity, so I do C equals that recursive call, it returns a tail call. Then I do, okay, well, it's still a tail call, so let's apply the function to the arguments, returns, apply the function to the arguments, returns. And then at the bottom, it's going to, when it hits the base case, it's going to return a lambda that I've been constructing this whole time, but only one level, right? So I do one level of lambda. And I kind of spoiled it. But if you notice the little pattern of the control flow going 0, 0, 1, 0, 2, 0, that's exactly why this is called trampolining. Okay, so CPS moves the remaining computation to data, and trampolining moves tail calls to data. Or in other words, trampolining is kind of the answer, the full answer to the old adage of recursion and iteration are two sides of the same coin. That's how you actually convert between the two, right? And if you take this even further, you say, I don't want any functions at all. Then you get defunctionalizations, which moves closures to data structures too. Okay, number two, lifting the recursion limit dependence. So 1 minute, oh my God. Okay, so we're writing an interpreter in language H for a language G. And what aspects of G semantics are independent of H? And so this is some stuff we've known for a long time. If you do CPS, the evaluation strategy is independent. If you do defunctionalization, higher orderedness is independent. And if you do both, then both are independent. And this is stuff we've known since the 70s, right? But something people don't talk about as often is if you want to make the recursion limit independent, just do trampolining on top of CPS. And then, of course, you can do all three transformations, and it's independent of H, the host interpreter language, on all three axes. And this makes trampolining, this is regardless of whether or not H does tail call elimination. You might argue that CPS is all tail calls, so it should be independent. But no, actually, if H doesn't support tail call elimination, then you need to do the further step of trampolining to actually get this to work. Yeah, and so trampolining is runtime tail call elimination. That's my second perspective.